Hello, so let us talk now about minimum spanning trees and how can we make a minimum spanning tree given a graph. So let's start with the definition or motivation. So a minimum spanning tree of a simple connected weighted graph now is a spanning tree such that the sum of weights of all edges is minimized. Okay, so what is a spanning tree? Spanning tree is a tree which has all the vertices of a graph without having a simple circuit or cycle. And a minimum spanning tree is chosen from all the possible spanning trees of a graph such that the total weight is minimized. Now, this can or cannot be unique depending on the weights we have. And we will see that if all weights are unique, then minimum spanning tree is unique too. Okay, so this is minimum spanning tree. The abbreviation or acronym we sometimes use is MST. Okay, so what are the algorithms? There are several algorithms, but two most common algorithms are the Prim's algorithm and the Kruskal's algorithm. So let's just briefly describe what's happening in both of these, and then we will do an example followed by the pseudocode of each of them. Okay, so for Prim's algorithm, we start with any edge with the smallest weight, and we repeatedly add edges of smallest weights which are not into the tree, that are adjacent to the vertices added to the tree so far, and they do not form a simple circuit. And we stop when we have v minus, the number of vertices minus one edges in the tree. So why do we stop here? We stop here because another definition of spanning tree is what? A spanning tree is a subgraph of graph G so that it has number of vertices, one more than the number of edges, and without a simple circuit. So when we have this number of edges, automatically we will have a spanning tree. And if we have ties, we can use any arbitrary ordering or rule which we can define ourselves to resolve that tie. Similarly, uh, not similarly, for Kruskal's algorithm, it's very similar to Prim's algorithm, but some key differences. So we start with any edge with the smallest weight. This is the same as the second one. But then when we repeatedly add edges, but this is the condition of adjacency to the currently formed tree is not there here. So repeatedly added edges of smallest weights still not added to the tree, that do not form a simple circuit. So no restriction adjacency. Okay, okay. And then again we will stop when we have the number of edges one less than the number of vertices, and again ties can be solved arbitrarily. Okay, now this is just simple explanation, and this is a very common sense kind of an algorithm. Both of them are greedy algorithms. So greedy, both of them. Okay. Okay, so let's say we have a graph like this. We have A, B, C, D, E, F, G, H, I, and we have this is. Now let's say if we have Prim's algorithm. So how do we add? So first of all, what does it say? Any edge with the smallest weight. So the edge with the smallest weight is e to the EF, not e to the F, EF. Okay. And then for EF, we have options of this is an adjacent edge, this is an incident 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 edge. Okay. So how many choices we have? We have CF and EH. So we can, because this has weight 3 and this has weight 3. All of the others have weight more than 3. So we can choose maybe EH. Okay. So then we have EH. Then we can choose HI because HI is the minimum weight possible here. Then we can choose CF. Okay. Now, do we have any other option here? We do not have any other option here, so we can choose CF. Then we can choose BC. Then we can choose BC. Then we can choose BD because it's adjacent again to the tree formed so far. And then we can choose DA. And then we can choose GH. Okay. Now note that how many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8. Now we have 8 edges and we have 9 vertices. So now we stop. Okay. So then we have a graph. So let's draw this graph. So we have E, let's say E is the root. So E, F, then E, H, then H, I, then C, so this is E, then CF or FC, then BC, so CB, because it's undirected, so BD, then BD, and then DA, and then GH. Okay, so this is my graph, and then I can put the corresponding weights here. So this is my graph, which is actually a spanning tree, which has the minimum weight here. Okay, so nothing with Kruskal's. Okay, so again, so first of all, what we do, we say EF because it's the minimum weight. Then the next minimum weight is HI, or I can choose AD as well, because both of them, if added, they do not form a simple circuit. Then we have BD, then we have EH, then we have CF. Again, ties can be resolved. This is not important. You can put AD before HI, you can put CF before EH, and so on. And then BC and GH. Okay, so now let's see how does this tree look like. This tree will be, so EF is here, so EF, and then HI is somewhere here, HI, then AD is somewhere here, AD, then BD is somewhere here, so BD, then EH is somewhere here, so EH, then CF, so CF is somewhere here, so CF, then BC, so BC is somewhere here, and then GH is somewhere here. So if you consider this as root, then this is the graph here. Or you can choose E to be the root, and it's exactly the same as we drew for the Prim's algorithm. Okay, so this is a small example of Kruskal's algorithm. Now let's say if we have to program it, both of these algorithms, and we have to see what the pseudocode is. So the pseudocode of Prim's algorithm goes like this. It's very self-explanatory. It is just language translation from the description to the pseudocode. So we have an input, we have n vertices here, and we start with a tree with only one edge with minimum weight, and then we say from I is equal to 1 to n minus 2 because one edge is already added. We say that E is an edge which has minimum weight among all the incident edges with T, because this is Prim's, that is not forming a simple circuit if added to T, and then we add this edge to T and we keep on adding until we have n minus 2 more edges added, and this plus n minus 2 will give us n minus 1 edges. The only difference in Kruskal's algorithm is what? We start with an empty tree and our loop goes from 1 to n minus 1, and this condition is that there is nothing saying about incident edges here. Okay, so a minimum weight edge among all edges in G that do not form a simple circuit if added to T, and then we add this to T. So this is it about the pseudocode of both of them. So this is about spanning minimum spanning trees and a brief explanation along with an example of Prim's and Kruskal's algorithms. Hope it was easy to understand, and thanks for watching. Hope you liked the video.